A bright marker moves steadily around the rim of a precision rotor. Watch the cyan carriage below it. The carriage slides left and right, always staying directly beneath the marker. Now watch the mint carriage at the side. It rises and falls, always level with that same point. Nothing pushes the marker sideways or vertically. The marker only travels around the circle. Yet each sensor reports a smooth back-and-forth motion. One circular journey is somehow producing two straight-line motions. What quantity is each sensor actually measuring, and why do both readings repeat? Pause the instrument at one ordinary position. The fixed point in the middle is the center, which we will call O. The rigid arm from the center to the marker is the radius, R. Its length does not change while the rotor turns. We also need a reference direction, so use the positive horizontal ray pointing to the right. The opening from that ray to the radius is the angle theta. Theta records orientation. It tells us where the radius is pointing, not how long the radius is. Now let the vertical sensor reveal its construction. From the marker, drop a line straight down until it meets the horizontal axis. Vertical and horizontal directions meet at 90 degrees, so the small corner is a right angle. Without replacing any object, the horizontal projection, the vertical drop, and the original radius now form a right triangle. The triangle was hidden in the instrument all along. It gives us a way to measure how the marker position depends on theta. Stand at theta and name the sides relative to that angle. The vertical drop lies across from theta, so it is the opposite side. The horizontal segment touches theta, but is not the radius, so it is the adjacent side. The radius sits opposite the right angle and is therefore the hypotenuse. These names depend on the chosen angle. They are not permanent labels attached to vertical and horizontal. Keep theta fixed. If this triangle grows, do both sensor distances remain fixed fractions of the radius? Now extend a second radius along the same direction. The triangle will be larger, but the angle theta is exactly the same. Drop a perpendicular from each endpoint. Each triangle contains a 90-degree angle. One angle matches, and the right angles match. With two equal angles, the triangles are similar, the same shape at different sizes. That means one scale factor k multiplies every corresponding side: radius, opposite, and adjacent. Test the vertical ratio. In the larger triangle, opposite over radius becomes k times opposite over k times radius. The common k cancels, so changing the triangle size cannot change opposite over radius. So for this angle, every similar right triangle has the same opposite to radius ratio. Now test the horizontal ratio. Adjacent over radius becomes k times adjacent over k times radius. Again, k cancels. Triangle size changes, but adjacent over radius does not. So the angle determines two fixed ratios, one vertical and one horizontal, no matter how large the triangle is. Give the fixed opposite to radius ratio the name sine of theta. Give the fixed adjacent to radius ratio the name cosine of theta. Bring the original rotor back and call the horizontal sensor reading x and the vertical reading y. In this first quadrant triangle, opposite over radius is y over r, while adjacent over radius is x over r. Those are the ratios we just named sine and cosine. Now calibrate the rotor so its radius is exactly 1 unit. Nothing about the angle changes. Dividing by 1 leaves the measured distance itself. Sine of theta becomes y, and cosine of theta becomes x. The marker can therefore be written as an ordered pair. First the horizontal coordinate, cosine theta, then the vertical coordinate, sine theta. This direct coordinate interpretation belongs to a unit circle. If the radius were r instead, the coordinates would be r cosine theta and r sine theta. The triangle introduced the ratios in the first quadrant, but the rotor does not stop there. As the marker crosses the top axis, its horizontal projection moves to the left and x becomes negative, while y remains positive. Across the left axis, both coordinates change their roles again. Below the horizontal axis, y becomes negative. The physical side lengths of a right triangle are still positive lengths. It is the directed sensor coordinates that carry signs. At the rightmost point, the pair is 1, 0. At the top, it is 0, 1. At the left, it is -1, 0, and at the bottom, it is 0, -1. Through every quadrant, the same rule survives. The marker is cosine theta, sine theta. The signs come from where the projection lands, not from a new memorized formula. Release the rotor and let theta advance at a steady rate. The horizontal carriage starts at its maximum, moves through 0 after a quarter turn, reaches its negative maximum after half a turn, and returns through 0 after 3/4. The vertical carriage follows the same cycle, shifted by 1/4 turn. Pause at each checkpoint and compare the readings with the marker position. After one complete turn, the marker, the triangle, and both sensor readings return to their starting state. Let the rotor complete another turn, and the entire motion repeats. That return is what periodic means. A uniform circular projection produces a sinusoidal motion, the particular smooth oscillation that sine and cosine describe. A motion can repeat without following this exact sinusoidal shape. Now place a second identical rotor beside the first. Give both the same radius and let both turn at the same rate, but start the second one farther around the circle. Their projections rise and fall with the same size and repeat just as often, yet corresponding peaks arrive at different times. That fixed separation within the cycle is phase. Phase changes the starting place. It does not change the radius, and it does not change the rotation rate. In the compact description theta of time equals omega times t plus phi, omega tells how quickly the angle advances, while phi tells where the rotor was pointing when our clock called the time 0. Connect the horizontal sensor carriage to an ideal spring and mass. The mass can share the same position function, x equals r cosine of theta of time, as the horizontal projection. This is why circular projection is so useful in physics. It gives a clean geometric model for simple harmonic motion, rotating machinery, alternating signals, and many wave sources. But the picture must be interpreted carefully. The spring force can cause the mass to oscillate. A hidden mechanical circle does not have to be turning behind it. The two systems share mathematical motion even when their physical mechanisms differ. The model reveals the pattern without pretending that every oscillator is literally a rotor. Let the two projection histories travel across a recording strip. Their crests have the same spacing and height, but one trace is shifted because its rotor began at a different phase. Relative phase tells us how two cycles line up when we compare them. The same bookkeeping becomes important when physical waves reinforce or oppose one another. Phase will return much later in the mathematics of quantum states. That future idea is not a claim that a quantum state is a tiny mechanical rotor. We are carrying forward only the precise language for position within a cycle. Return to the original sensor mystery. At the rightmost point, the horizontal sensor reads 1 radius and the vertical sensor reads 0. After a quarter turn, those readings become 0 and 1 radius. After half a turn, they are -1 radius and 0, and after 3/4, they are 0 and -1 radius. We did not memorize a table. We read every value from the moving geometry. Now let the recording strip slide while the rotor turns. Each instant places one projection measurement at a new time, and the circular motion begins drawing a curve. We began with one point moving around a circle. Its vertical projection gave us sine, its horizontal projection gave us cosine. Radius controls the size, rotation advances the cycle, and phase tells us where that cycle begins. Next, we will unroll the circle into time, discover why physics measures angles in radians, and watch these projections write their wave-shaped graphs.